I did notice, because as the author of the system, it was always clear to me whether it was a macro or a procedure call. And without looking at the index, you have no way to know right now. So probably it would be a good idea to have a little typographic symbol indicating it's a macro call or something.
Actually expand to the full web module names.
No. See, when you call a macro, I might even want to have indicated by a subscript, which tells me what's the module number where the macro was defined. That would be another way. If it would say Inker sub 3, then you'd know that was a macro because it has a subscript on it, and procedure names don't. So I like to experiment with that. It's a problem that I wasn't aware of until this week. Yeah.
Is Lasky trained to underline macro names or something?
No, I guess they've started to tape. So if people want to make comments, so we ought to do it for the people out in TV land. Well, let's continue this discussion later. This is 6 down and 6 to go, and our current this thing under discussion will be the paragraph maker, and a couple of we can talk about web later. Okay, put it in context again. We'll give this old slide, and I have another slide that you haven't seen before that you'll get to see in a minute. So the paragraphs, it counts for a little bit of code here, about, what is that, 100 modules, and if you add hyphenation to that, which is about the same amount of code, this is the thing that takes place when a horizontal list has been finished and it's time to break it up and put it into boxes of the H size. It's a self-contained little part of the program that only gets called in two places. Once it gets called when you have finished an ordinary paragraph, and the other place is when you've started a displayed equation. In both cases, you take the previous lines and make them up into paragraph. There's one of the things in the state. Remember, we had the mode and the head and the tail and the space factor. There's another thing in the state called already, and this keeps track of how many lines you've already set for a paragraph. In case of a displayed formula, you have to resume maybe at line 8 or 9. And the reason is that paragraphs can have hanging indentation, and the hanging indentation might say go on for the first 10 lines, and so you have to remember how many lines you've already done. In TeX, you know that you can also play games with paragraphs, and you can get different shapes, something like that, and specify the paragraph shape. So it's another reason why we want to know how many lines we've set. You could have a displayed equation in the middle of such paragraphs. What TeX actually does is it considers a displayed equation as 3 lines long, and all 3 lines are equal in size to the middle of those 3 lines. Usually the first and last are blank, and the only time that you have other lines is if you have to drop an equation number or raise an equation number. Now there's tiny little numbers in the right-hand margin here. This is the glue ratio that had to be used in that line. If you could read it, in the first line it would say 0.305, says that these spaces are a little larger by 3/10 of their stretchability. The next one 0.867. Here's a where's a minus? Yeah, the bottom one is a minus 0.517. And this is, in some sense, the optimum way to put those words into that shape. And we changed the text to other texts, and we could fit them in also. It wasn't particularly difficult to do this example. We didn't have to fudge with it or anything very much. But the question is, what kind of algorithm is actually used to make paragraphs? And it's one of the most interesting algorithms in TeX, probably the most interesting one. And it's due in major part to Michael Plass, whose wife you all know because she's been our host this week. Now, Let's first talk about the case where we don't have a paragraph shape and all the lines are the same length. This diagram indicates one of the tests that we have carried out over and over again to our favorite text. This is the text taken from Grimm's Fairy Tales, and the only reason we did this is that for some reason somebody put Grimm's Fairy Tales online in the SAIL computer system. And this is fairy tale number 1 and the first paragraph of fairy tale number 1. If you want to read the rest of the fairy tale, I have it online and we can look at it later. And all the other tales are on there too. And we also have Wuthering Heights, but I don't. And we have. Oh goodness, what was Colin Higgins' first movie? Harold and Maude. Yeah. Okay. So those are the books that we have online, and we can do our experiments on paragraphing with those things. And also, there happens. I guess the Art of Computer Programming is online now. Well. In olden times, when wishing still helped one, there lived a king, and so on. This is the paragraph, and the question is, what's the best way to put it into a paragraph? And TeX has its way to define best in terms of concepts of badness and demerits. Now, badness is something that depends on that little glue ratio number that we had on there. This one is so smeary I can't even read it off of the slide, but it's 0.7 something on the top line. Now the badness is in simple cases is equal to the cube of that number times 100. So if it's 0.7, we cube it to get 0.49, and then what? 343 is 7 cubed, so 34.3 units of badness because we multiply by 100 afterwards. Now this 100, of course, is an arbitrary scaling factor, but then we convert to an integer. And this calculation of badness is actually done by, like all the other things with integers, by some precise method that you're not allowed to diddle with. So the actual calculation of getting that thing, we didn't compute the glue ratio with floating point arithmetic. We had the true integer number of scaled points that we wanted to expand that line by, and we had the true integer number of stretchability that we could do it, and those two numbers were computed by a subroutine called badness that will produce probably the number 34, maybe 35. But whatever number it produces, every implementation of TeX is supposed to produce exactly that same number. And it's pretty much the ratio of the 2 cubed times 100. And the reason that number was chosen was because it has the right properties for that we were looking for, namely it stays close to 0 for a while, but then it starts to rise rapidly after things start to get real bad. Then once we have badness, we add on to that another number called the line penalty, which just says that any line has a certain amount of has something wrong with it, just because we don't want to waste lines. And so line penalty in TeX, the old version of TeX, was always fixed at 1, but in TeX82 you can say the line penalty is 100, and that'll make TeX a lot less happy to make a paragraph longer. It'll try to, the larger the line penalty, the shorter the paragraphs will tend to be. And then it's funny, if you try to set line penalty negative, strange things will happen, and well, let's not muse about that for some. Anyway, there's a whole bunch of other parameters that can be played with. So many that I doubt if anybody will ever be able to experiment with very many of them in their lifetime. I mean, there's just that many possibilities to try. So you find ones that you like and live with those. But the line penalty is one of these parameters. So we take the badness, compute it as I told you, and we add the line penalty. Then we add penalties associated with this particular kind of a break. So if there's a break at the end of a line that's due to a hyphen, then you add on the hyphenation penalty. There's two kinds of those. There's the kind that was a discretionary hyphen, and there's the kind that was an explicit hyphen, like if somebody has a dash or a real hyphen in his text where he said nitty-gritty or something, and there was a hyphen there in a thing, and that's an explicit hyphen, that gets one penalty. The kind that had to be inserted, the hyphenation algorithm, that gets another penalty. Anyway, that penalty would be added. Or if you broke because of an explicit penalty that you said penalty 100, then the penalty is, of course, 100. Now, we calculate the demerits of a line by taking this badness and the line penalty and the other penalty, and add those all together and square it. And that's demerits. And the more demerits you have, the worse you're off. Now, on the other hand, if the penalty is negative, for example, if somebody said break here with penalty minus 100, then we don't want to subtract 100 and then square it, because that's going to go the wrong way. So in that case, we compute the square of the badness, and we subtract the square of the penalty. Now, these are arbitrary formulas, but they tend to agree with what we're supposed to do, namely, as the penalty gets larger, this demerits go up, and they tend to produce the right results. So we had to have a way to find a quantitative statement. How much does it cost you for certain effects in the page? So the costs are computed by a mathematical formula. Finally, we get to a notion of demerits, and the idea is to find the way to break a paragraph so that the total number of demerits is as small as possible. Now, in this particular example, we can illustrate that problem by this neat little chart here, where I draw on each line the number of demerits that would be associated with a line from a break at this dot means the beginning of the paragraph. Here's a break after the word A. So on the first line, which had 0.7 something of badness, so that would be 34 and so on, and after squaring and everything, it turned out to be adding line penalty and squaring and so on. It turned out that it was 2,357 demerits for that line. On the other hand, if we brought king over to the end of that line, it would have fit, and it would have been only 1,734 demerits. Okay. Now, similarly, what about if you stopped after A and just considered from dot to lived? I didn't even show that on here. It's not because the demerits are so large. The reason I didn't show it is because there's something that TeX calls the tolerance, and which the old version of TeX called the J-par, which says anything that has to stretch too much is not considered at all. And so we say that a line break is feasible if there's a way to get there from the beginning of the paragraph without violating any of these tolerances. Say that again. It's feasible if you can get there without violating any tolerances. Now, I've drawn blue lines for all the feasible breaks in this paragraph. So you notice at the beginning we had a feasible break after and after king, but whose would have made it too tight, lived would have made it too loose. And there's a sort of a V-shaped effect that as further on you get into the paragraph, the more breaks become feasible. And if your tolerance was very sloppy, this was done with tight tolerance, where we had much more rigid spacing controls than publishers generally do use. So if we gave ourselves a lot of tolerance, then we would probably had all blue lines after we got down 4 or 5 lines into the paragraph. In TeX82, if you make the tolerance 10,000 or more, everything is feasible. And tries everything. It wouldn't mind going in space Olden all the way to the end. Okay. So there's a notion of infinitely feasible. But the tolerance is typically 200. That means in units of badness. Tolerance is now given in units of badness. It used to be given in another way, but tolerance now is given in units of badness. So if I set the tolerance to 200, that means that I'm not going to accept any line whose badness is more than 200. This means it would stretch more than cube root of 2 of its stretchiness, because cube root of 2, when we cubed it, would give us 2, and then multiply by 100 to get 200. So feasible breaks are shown here, and every time I have a blue line, I have a corresponding box down here. And so the question is, what's the best way to get from the beginning of the paragraph to the end in the sense of total demerits being small as possible? This translates into another well-known problem in computer science, the shortest path problem. What's the best way to get from here to there in the sense that the total distance should be as short as possible? So if we knew all the feasible breakpoints and we knew all the demerits between feasible breakpoints, then we apply shortest path algorithm, and it gives us the shortest way to go. And this one on the top is the shortest way. So it's why we come down through instead of going through king, because even though it took more demerits here, we're going to win pretty soon by picking up only 6 here, where that one has to pick up 4692 in the next line. And by putting king in there, you get stuck on the next line. You don't have as good a chance. So in this way, TeX is able to use the paragraph as a whole to get the best way to do the breaking. And we use this in the first TeX it was successfully used for about 2 years before we realized there was a bug in it. Well, before I discuss about the bug, I should mention that how is the algorithm going to go on? We don't simply go through one pass through the paragraph, note all the feasible breakpoints and demerits, set up this graph, and then start up a shortest path algorithm. The whole thing is all done on the fly simultaneously. So as we're going through the paragraph, we're keeping track of as much information as we need to be able to recognize a feasible breakpoint when we come to it. And at the same time as that, we're also doing what the shortest path algorithm would do on an acyclic graph like this. Now the bug that we noticed sometime after is illustrated on this chart, and the one on the right-hand side is the way it would have been done by our first algorithm. And the slide sort of explains the problem itself. The bug only occurs when the line width changes, and here we have an example where the line width changes. And we had been keeping in our diagram for each feasible breakpoint, we had been keeping track of the best way to get from the beginning to that breakpoint. But we hadn't been keeping track of the best way to get from the beginning to that breakpoint on line 10 as different from the best way to get to that breakpoint on line 11. But it might be possible to have the paragraph be feasible both ending at one place at line 10 and ending at line 11. Okay? So for example, in this case, at the end of the word like, there's two, on the left-hand side, like fit okay, way at the end of the indentation there. Well, it also fits on a line above. In fact, you can probably squeeze it up somewhat higher and find a way to do it feasibly. We set tolerance very high in this particular example. So what happened was, in our old algorithm, keeping only the information for breakpoint and without considering line number, we would say that it was the best way to get from the beginning to like would be that way. And then when we come to this long equation on the next line, and it says now what to do, well, there was no good way to do it because we had lost track of the fact that there was a feasible way to get to this on another line. We only kept track of the best way, some of you might see the problem then as to how our algorithm forgot that there was a feasible way also to get like at line 11. With each breakpoint, we stored the best way to get there and the line number on which it would be at the best way. We should have done, for each combination of breakpoint and line number, store the best way to get there. So the algorithm that's in the present version of TeX has that bug fixed and does the thing on the left. Now I showed this to some printers and they said the spacing is so wide on the thing on the left they would still prefer the one on the right. Well, okay, anyway, it was a bug. So now those are the only slides I've got for you on that. Question? Jan?
On the last slide, you mentioned that you'd keep a feasible way to get a certain break at a certain line. Is there a way also to figure out a feasible break at arriving at a certain distance down if you don't know what the line width spacing is going to be on the way?
Yeah, this generalization has been developed by Iñaki in his PhD thesis, and he's generalized this algorithm so that it will deal with shapes, putting text into shapes. To me, it's amazing that it could ever be done, but the other day he convinced me that it would work. That's one of the many things that he's doing in his thesis. Now, the thing I told you about demerits isn't quite complete. There's also extra demerits thrown in for, let's see, what is it called? Double hyphen demerits is one of them. There's a parameter in TeX82 that you say, how many demerits do you pay for double hyphen, 2 hyphenated lines in a row? And so you add to the demerits that I've already told you how to calculate this extra penalty for double hyphen. There's another one for final hyphen demerits. This applies if you are if you're at the end of the paragraph and the second last line of the paragraph was hyphenated, and that's a separate separate calculation added on to demerits. This is called demerits rather than penalty because it doesn't get squared like penalties do. Now, there's also the adjacency demerit, and this is when you have a tight line followed by a loose line, or vice versa. You pay a penalty for incompatible lines consecutive. It's sort of better if you're going to have a tight line somewhere, then you don't want to have a loose line right afterwards. It's particularly noticeable when there's a dramatic switch. So there's a calculation based on a bunch of parameters the user can supply, which then leads to a shortest path calculation where we try to find the shortest path. The fact that we talk about tight lines and loose lines means that we have to improve the algorithm still further along the lines of this bug I mentioned. Namely, we have to remember for every breakpoint, for every line number, and for every class of fitness, so whether it was tight or loose on the last one, we have to remember what's the best way to get there. That triple of things is really what we have, are really the vertices in our shortest path algorithm. Now the idea then is going to be to keep a data structure that represents enough information for us to do all that. And we do it in terms of so-called passive nodes and active nodes as we're going through. Now, as we begin at the beginning of the paragraph, maybe I ought to put that slide up on the screen again. First, I'll wave my hands, and then I'll tell you a little more detail. So, how do we actually generate this all on the fly? We start out, and there's one active node, one active breakpoint, and it's for the beginning of the paragraph. And the list of active breakpoints contains only that thing. Then, whenever we get to a valid break, we start searching for the paragraph, and every time we get to a space between words here, that'll be a valid breakpoint, and the subroutine called try break is called. And try break looks at every active breakpoint, and every active breakpoint, at first there's only this one. It tries to see, well, what about the best way to get from the beginning of the paragraph to the current breakpoint via the active breakpoint. Now, the only way we're ever going to get to, so suppose our current breakpoint is called P, then we want to get from beginning to A to P, where A is some active breakpoint. We've already recorded the best way to get to A, so we can figure out the demerits from A to P, and then we know the cost from beginning to A to P. the best possible way from beginning to A to P has to be the best possible way to A, followed by A to P. A also includes whether it was tight or loose. This is a slight subtlety, and it also includes at what line number there is. But I'll for simplicity, just talk about breakpoints. So we look at that number, and for all A, fixing P, and for all A that are currently active, we take the one that turns out to be best. And if none of those is feasible, then we throw P away and nothing ever happens. But if at least one of them is feasible, the best one gets considered an active breakpoint, and and then we'll start testing it against other things. Now, if we find out that there's some active breakpoint that's so far away from P that from A to P causes us to exceed the shrinkability, so that we could never fit the line from A to P in to get the current line, then A becomes inactive. We take it off the active list. I have to mention, I hope that works. I believe that, yeah, that must be okay. Yeah. Because A has a certain line number associated with it, and it would still remain active at other line numbers. Now, in this case, then, what's going to happen? We'll start out with this one active, and after we get to A, that one and A will be active. After King, we'll test King against this one and this one, actually. And we'll find that the best one is from the first to King. Then when we get to Whose, we're going to find out that this one should be retired. So this one becomes inactive, becomes passive. And finally, when Was occurs, we'll find that Was should become active, and So occurs. Okay, then the next word after So, beautiful, A is now going to be no longer active, nor King. And so eventually we'll only keep a few active nodes at a time. So the search is the number of the time to do this algorithm is proportional to the number of breakpoints times the number of active nodes. And the number of active nodes tends to be, at worst, the number of words you can have in a line. So the algorithm runs quite rapidly, and even when we're setting unusual paragraph shapes, we can get the thing that's globally optimum for the paragraph as a whole with a method that is only slightly shorter. Slightly slower than what you would do if you were just setting a line at a time on the fly, as in other systems. Let's see, I wanted to make another quick point, but what was it? It flashed through my mind. Oh, I just wanted to say it's amazing when you play with this and you see you correct a typo in the last line of a paragraph, and then all of a sudden something else shifts up in the first line after this algorithm goes on. It also does amazing things when it goes wrong, as we discovered. For example, a mysterious problem was happening on the current membership list with the American Math Society until we found out that it was because of the final hyphen penalty. The line before the last line was hyphenated, and it wasn't choosing this alternative as the best one, although it looked obviously better to us. Because we didn't realize it was the line before the end of the paragraph. In the current membership list, they ended the members' entries with like A for association, and I for the Siam, and S for the society. And so the person name given here, and then at the end it says some stars and SAI. Here would be the hyphen, but TeX wouldn't like this solution because we hadn't realized that the final hyphen penalty was acting there. So it would prefer setting something without hyphenating that word and bringing something over here and making it look this way, and it surprised us. So there's there's a bunch of parameters in there, and if you look at the code, probably each parameter just appears once in TeX program, but the art of using these parameters is something that can be learned, but takes a little experience. I think it's fun to watch it. Now that I said that we have active nodes and passive nodes. Actually, we make up a passive node at the same time as we make an active node, and then when the node becomes inactive, we just recycle the active node part. The passive nodes are very short. For every feasible breakpoint, we have a passive node that's 2 words long. And in fact, it could only be 1.5 words long if we were working on a 16-bit instead of a 32-bit machine. Active nodes, I forget how long they are, 3 or 4 words long. Each active node points to the corresponding passive node, and also has these values on it, like the total demerits, the best total demerits to get to here. And it will contain other things in it, like the line number, the fitness class, whether it's tight or loose, and this one points to the breakpoint P that we're actually trying. The breakpoints that we might find are at glue nodes, or at discretionary nodes, or at penalty nodes, and then in special cases, math or current node. If you write a math formula and it says, say, X, and somebody has used a math surround option in TeX, which says that he wants every math formula to be surrounded by a certain amount of space, well, then you could break at this surround here. Namely, if a math formula is immediately followed by a space, it's valid to break there. And so that X would be flush right. Similarly with kerns, if a kern is followed immediately by a space, it's allowed to break there. So those are the kind of legal breakpoints we have, and that's what P represents: something in mem that's either a glue node, or a penalty node, or a discretionary node, or math or kern in these special cases. The difference between TeX new algorithm, TeX82's algorithm, and the one in the present TeX is primarily that in the present TeX these were both combined in one big 10-word node. It was taking a lot of memory, and what we did was, when it became inactive, we just moved it to a passive list. And I just noticed when I was recoding it that we weren't using many of those words anymore. So now I just make it up with the part that I'm going to need at the end, putting immediately on a passive list. The passive list points to P. It points to the best previous node from P. In other words, the best way to get to A was from some other passive node. And it points to the previous passive node so that we can at the end recycle all the passive nodes to the available storage. So there's 3 pointers in every passive node, 1.5 words worth. Active nodes contain the total demerits, and they also contain things like the line number and I mentioned. Now in the existing version of TeX, we also kept track of the total length of everything from the beginning of the paragraph to here. If you imagine the paragraph all stretched out in one straight line to the given point, how much was there? And we would use that to calculate the badness of a line, because if we knew the beginning to A and the beginning to B, then for a line from A to B, we subtract those 2 numbers. Well, those 2 numbers were kept in floating point notation. And they included, and there was also a similar thing for stretchability and shrinkability that we would keep track of in floating point notation, so that we could determine between A and B how much stretchability there was between the line, as well as how much space there was between those 2. We want to get rid of floating point arithmetic in TeX82, and it also led to other problems in the present version of TeX. If you ever get this error message that said too much stretch for proper line breaking, this is because when you took the glue up to B and subtracted the glue up to A, you got infinity minus infinity, which canceled out to 0. It didn't give you very much information as to because the floating point arithmetic, all the what you needed was wiped out. The significant figures had the number of fills in the paragraph, but not the details that you needed for line breaking. So that wasn't working properly, and the only way to fix it would be to and continue that same algorithm would have been to make these active nodes very large, keeping track of how much glue there was of type fill, of type fillable, and so on. And each of these another 32 bits for each active node. But still that wouldn't be good enough, because if you had a large enough paragraph, you'd overflow. I said the other day, well, who's going to be caring about dimensions that get larger than 17 or 8 or wherever somewhat feet is concerned? And it's true that B minus A would never be 17 feet, but from the beginning of the paragraph to a given point might very well get quite large. In fact, we've had cases where we've seen paragraphs that run over 3 pages, and you know, we're trying to find the optimum way to break those pages. By the way, if you do that, it fill memory in another way probably, and you can. And you saw the triangular effect of these feasible lines. So after you get into about 30 lines, you could just arbitrarily say, okay, break it here. This is going to be a good place to break, and get rid of this paragraph. But certainly I didn't want to worry about overflow. Calculate total length up to here. That would be, even on reasonable paragraphs, this would give arithmetic problems. So instead of that, I keep track only of relative distances, and the distances from the first active node to here is that I keep. So I keep track with the first active node to here for every node, and then in my active list I have 2 kinds of nodes. I have an active node, another active node, and then I have called a delta node, and then another active node. Let's say A1, A2, A3, and so on. So delta nodes can also be in the active list now, and these are nodes that tell me this is the difference between from breaking at A2 to breaking at A3. So when I pass by a delta node, it tells me it gives me the right information for relative distances relative to A3, while before I had relative distances relative to A2. So this is an extra feature was added to the data structure in order to avoid the problem of multiple precision arithmetic, and also making all these active nodes larger. But the expense of that was several more modules of code and several more days of debugging time, but it should run fast. Now delta nodes are in there for this calculation of that I need to figure out the badness. As you go, then let's see if we can put ourselves in TeX shoes. It's trying to determine whether P is a feasible breakpoint. It starts at the beginning of the active list, and it has in some table already the length of the line from A to P, from the first node in the active list to P. Then, okay, so it can then compute the badness and see if it's feasible, and then move to A2. If it passes a delta node, adjust its tables of the distances, and go on. Now there's still more details to take care of when you do this, because you have to remember that when you break at the end of a line, the glue after that break disappears. And so you really are considering, when you want to figure out the distance from a break at A to a break at B, what you really have is B. Well, I think I call it alpha of B. No, see, B minus alpha of A is the distance from. Now this means the distance from the beginning of the paragraph to before B, beta for before, and alpha for after, to a place after A. So if you have your paragraph laid out here, and here's B, some glue say, and here's A, then the length of the line is going to be from the point after A up to the point before B. It's not just the distance to B minus the distance to A. It's the distance to before B minus the distance to after A. And so there's that little difference in there. Okay, so the delta node that we put in here is really alpha A2 minus alpha A3. Because we're assuming that we know when we're at this point we have beta of P minus alpha of A2. And then when we pass the node, we want to get beta of P minus alpha of A3. So the correction delta is equal to alpha A2 minus alpha A3. That's the way you derive these formulas. So this is the length of the line that we can then compare to the true to the desired length of whatever line we're worried about. If the break is at a discretionary node, for example, a simple case where it's a hyphen or not a hyphen, then we have to take into account a breakpoint here. We have to say that the break before the hyphen covers a certain amount of text, and the break after the hyphen is a certain amount of text. And the meaning of this notation, beta and alpha, has to be properly defined for discretionaries. And I went around about 3 iterations before I finally had that one right. Now, the actual width of the line isn't exactly this, though. There's another constant has to be thrown in because TeX82 has introduced left skip and right skip, which are added to every line of a paragraph. This makes things like ragged right setting and centering very much simpler, but it also meant that in my calculation I have to add this background information gamma, which is the sum of the left skip and right skip, and that gives me the true size. So with all these qualifications, you see, the idea is we start out with some fairly simple ideas and add one or more complication after another until you finally get something that can only be described in web, I think, with any hope of possible success, because web allows you to describe one idea at a time and string them together. Otherwise, everything is really too involved putting it together. Now, okay, what more should I say about this except that we want that it is part of the inner loop, so we also wanted it to be fast. And I calculated that the hyphenation algorithm would not have to be applied very often. This is quite important to the efficiency. So how do we handle this problem of hyphenation? Well, here's the way it goes. The algorithm goes in 2 passes. On the first pass, no hyphenation takes place, and instead we just keep on trying the algorithm, seeing what we can do, try to get the best result, and unless the active list becomes empty. Now, in the diagram that we have there, every time I get to one of the feasible breaks, there was always some escape out from below it. That's not always true. You could certainly get to a place where it'd be feasible to get up to there, but nothing feasible after that point. And then, if you were in a conventional typesetting system, you'd be stuck. You'd have to have a really bad line. And here, you can imagine backing up and going down another route. But we simultaneously are covering all bases as we explore we keep track of all the active nodes, all the leads at once. But sometimes all of your leads disappear. You got nothing active anymore. You're stuck. Okay, then you go to the second pass. The second pass tries hyphenating to get out of it. And every word is hyphenated. Every word that meets certain conditions is hyphenated. The first condition is that it's got to be at least 5 letters. There's no point in trying to hyphenate a 4-letter word because TeX is not going to hyphenate ever after the first letter or less than 3 letters after. So TeX will never hyphenate a hyphen something or other. and it will never hyphenate something ED. It'll always put 3 letters after the hyphen and 2 before. So that means that you've got to have at least 5 letters, so why bother trying to hyphenate a 4-letter word? If the word starts with an uppercase letter, you don't try to hyphenate it unless the parameter uppercase hyphenation is set on. Right now we're putting it on by default, though, because the algorithm seems to work a lot, much better than we thought it would on uppercase words. If there's something, if you're in the middle of a math formula, you don't try to hyphenate. So there are some conditions have to be satisfied, but otherwise, every word passes this test, and we have to submit it to the hyphenation algorithm. Well, the nice thing was that in the entire book, Art of Computer Programming, Volume 2, 700 pages worth of stuff, we could test this on thousands of paragraphs, and we found out that the average number of hyphenations we had to try was 1.2 per paragraph. That was because only one time in 12 did we have to go into the second pass. So most of the time we could go through on the first pass, find a feasible way to do the paragraph without hyphenation, even though our tolerance was extremely high, so that we had the tolerance so that no really bad spaces would be allowed at all. The hyphenation then seems to be kept down to not really considered in inner loop. But if we do have to hyphenate a word, and then the next lecture will be about hyphenation, if we do have to hyphenate a word, then the hyphenation algorithm just returns the word with discretionary, the same thing, the list is replaced by another list that puts in discretionaries instead, in place of the word. So then TeX proceeds to go through the new list with its discretionaries in it, just as if that was given to it by the user, and applies the same algorithm. On the second pass, you might say, where do overflow boxes come from? And that I can tell you, that's in the second pass. We never allow the active list to become empty. If the active list becomes totally empty, we'd be sunk. We'd have because at the end of the paragraph we have to go through the passive nodes. And well, I'll tell you about the end of a paragraph in a minute. But we lose all contact with the paragraph if the active list becomes empty. So there's a time when we determine that we're just about to lose the active list, and at this point we leave something active even though it's not feasible, and that's where an overflow box becomes created. Now, the test for when that happened, I might as well find the module exactly where it is, but that was the source of the most difficult bugs in the present version of TeX, and I changed that at least 4 times before getting it right. If I had to say that there was one really subtle part of TeX to name the one that was the hardest for me anyway, it would have to be that particular one. And let's see if I can find it. Let's see. Dare not lose all active nodes. Here's 744. During the second pass, we dare not lose all active nodes lest we lose touch with the line breaks already found. Code shown here makes sure that such a catastrophe doesn't happen by permitting overflow boxes as a last resort. Then it says readers who seek to improve TeX should therefore think thrice before daring to make any changes here. This little test, if second pass and minimum demerits equal awful bad, and link of R is last active and prevar equals active, all 4 of those were added one at a time, I think, and replacing some other ones. Then I changed the badness to 0, and it might take me a while to reconstruct exactly all the reasoning behind that one line there, but the computer, of course, doesn't know that it was hard to think of, so the computer will just go as fast as ever when it gets there. But when we're reading it, we might stop a minute to think why did it do that? Okay, that was the part where the overflow boxes come in too. And of course, if somebody doesn't want overfull boxes, by setting the tolerance to 10,000, you don't get any. You just get underfull ones when there's nothing there. I found that for my purpose, it was much better to see overfull, because then I could see where how much room there was. I wanted to make a change anyway. I didn't want to leave a glitch in my final output. If I don't care about glitches, I set tolerance very high. But if I do care, then I want to see this overfull box, because I can look right at it and see how much it will fit. Otherwise, if it's stretched that one and put the carryover word on the next line, I have to try to estimate the sum of all those spaces on the previous line and how much they would shrink down and how much room I have. This is a visual way to really see what kind of correction to make. Now, I mentioned we got to figure out what to do at the end. We come to the end of the paragraph, and then the thing is to actually make the boxes. So at this point, we've got a whole mess of passive nodes. Like for every blue mark in that line, we've got one of these little passive node boxes. And these are all strung together by links, each one pointing to the previous one, just so that at the end I have a pointer passive to the last one, and at the end I'll just recycle all these nodes by going through these links, and they all get sent to available storage. But they also contain pointer to the breakpoint where they are, discretionary or something like that, or a glue or something, and they also contain a pointer to the best previous place to go. So this one will say the best one for that was here, best one for that was here. So let's go over to this slide. For example, at the end of a paragraph, the best previous thing from thing must have been her. So I would have a backlink from this one back to her. And from her, it would tell me back to ball. And so the pointer, you see, and the way I calculated those was as I was making the thing from the beginning, I would keep track for each of these. I would write down the minimum total demerits from beginning to here, and then the way I got to it. So what was the last step in that chain? So by going back from these backlinks, that's what tells us how to do the paragraph. And so at the end of the paragraph, I've got only one active node, and it's this one. Then I make it passive. When I look at the corresponding passive node, the passive node points me back to her. That passive points me back to ball, and so on. I'll reconstruct all of the setting, all of the lines as they're given there. So I have to reverse those links so I can do them in the forward order. So I go through, and I start at my best passive node. I go through, and I follow its length, maybe 10 lines, so it goes down to the best 9th line, 8th line, all the way back to the beginning. I reverse those links so that I now have the appearance of clairvoyance. The beginning tells me the best way was to go to this one, and these links are now going this way and telling me the right thing to do. So the remaining thing to do is take my horizontal list and break it up at these breakpoints. These things will indicate the 10 breakpoints as to where I ought to break the list. Subtle bug that occurred in here a couple years after the first TeX was apparently working well was that every once in a while we got a weird case where there would be a breakpoint with some glue, and then there would be some penalty after here, say, and then maybe some more glue, and this would be wiped out. Another penalty over here. So that usually when we break at glue, then we also cancel off all penalties that immediately follow it. But what actually happened one day was that this penalty turned out to be one of my best breaks, even though this glue was also one of my best breaks. And when I was going through boxing the whole thing, I broke here. I said, okay, wipe out all the stuff all the nodes after it here. And then I come to my next one, and it was supposed to go here, and I was out in my available space list and starting to point to nothing. And you can imagine all heck would break loose at this point. So now this So this is one subtlety that has to be. These breakpoints might actually point to nodes that are wiped out, but usually they don't. And usually that means that if it's glue, you wipe out the glue here and any penalties that follow it, and then you get to a box or a character that begins the next line. This becomes your next line. So here we get a box that you send to the HPAC routine. HPAC routine does like we did before when we made an HBox, computes the height and depth and so on. It will give the error message about an overfull box. And so we build now a vertical list. A vertical list containing the first line of text, then the baseline skip calculation is made between all of these, and for each line of text we build up another vertical list. Now the HPAC routine, as we send it a sublist of this original paragraph to be boxed, the HPAC routine not only calculates the height and depth and width of these boxes and glue setting and things of the box, but it also looks for insert nodes and v-adjust nodes that are in that box, and those nodes get appended right after the box. So it removes them from inside the box and they come outside the box. That's how the v-adjust and things like that get worked out. We also look for penalties. For example, between the first line and the second line, a widow line penalty is inserted here, so that there won't be a break between these two lines unless you pay the penalty for widows. There's a penalty for a break after a line that ends with a hyphen, so we also keep track of that as to whether or not there's a hyphenated, because we don't like to break a page. These breaks are for page breaks. So don't like to break a page after a hyphen if we don't have to. Yeah. Dan?
What about widowing lines at the top of the next page?
A what?
Widowing lines at the top of the next page.
Yeah. So the second last, the widow penalty is also inserted here. There's a final widow. There's a final widow penalty. There's a display widow penalty or not. This penalty changes depending on whether there's a displayed equation following or not. Some publishers tend to think it's much better. Well, I think they all think that it's infinitely better to start a line with a page with a widow before a display than to start with the display itself. And so that is a separate thing. In the present version of TeX, that's 0, but now it's a special parameter where there's no reason why we couldn't make. So we have a pre-display penalty or something like that. Display widow penalty, it's called, which gets added before a display, but otherwise this one gets there at the beginning and at the end. There's also interline penalty, which gets added to all of these guys. And that we recommend for footnotes. If you want to make people pay a penalty for footnotes, you pay the interline penalty plus the widow penalty for here in a footnote, and just the interline penalty in here. Anyway, those penalties are passed in vertical mode. This is now a bunch of boxes in vertical mode, and the page builder has to decide how to break that into pages. The page builder does it one page at a time on the fly, and uses a calculation much simpler than the paragraph builder, because it only has to look at the badness, not demerits. It only takes the badness for the current page and finds the place where the badness is plus penalties is as small as possible. The way this program is organized, then, the first section about breaking paragraphs into lines is section 37, module 704, and that is basically the try-break subroutine and all the details about how you calculate these delta nodes and keep track of maintaining the active list. Then section 38, breaking paragraphs into lines continued. That's the part that talks about running through the list, telling whether or not it's legal to break here, calling try-break at those places, and then doing the final packaging afterwards. The final packaging is done by a separate procedure because, again, this would have otherwise been a procedure that some Pascals wouldn't have been able to handle. Now I mentioned that hyphenation is actually as much code as breaking paragraphs, and that's the subject of the next lecture, which will start in a half an hour. Question though?
Are rivers considered all here, or they just don't occur anymore?
Yeah, rivers are not looked at, as you can see in this algorithm. I don't have a, but the experience has been that with good tolerances, rivers just simply are very rare. But rivers definitely show up when you have wide spacing and when you use the looseness. I didn't mention looseness. If somebody says looseness equals 1, then the algorithm will figure out the best way to get to the end of a paragraph and find out how many lines that took. Maybe it was 8 lines. And then it will find the best 9-line way. So we would run through the list at the end. At the end, all the active nodes are, the only active node is the end of paragraph node, and those are all stopped, or those are all marked with how many lines it took to get here. And so we can say the best way to get here in 9 lines, the best way to get here in 10 lines. And when you make the paragraph a little loose, then you'll find the best 10-line way to do it. And usually that looks fine. But then somebody says looseness 3, something like that. I don't have the slide here, but we can take this paragraph and set it with looseness 0, 1, 2, and 3, and minus 1. Actually, you can actually get into one fewer line. And by the time you see looseness 2, rivers start to appear. And this is typical of what happens if the but rivers also. So rivers generally go away, except there's another case where I've noticed them. We typeset a paragraph where out of an old newspaper which was listing the people who had attended a wedding. It was Mr. and Mrs. Smith, comma, Mr. and Mrs. Jones, comma, and so on. And you got a lot of misters lining up at the left-hand margin. So TeX doesn't keep track of that. That has to be manually broken. There's also theoretical proof that to eliminate rivers would be NP complete. I mean, it would be a very difficult problem to do it in the general case. And since we found that it was not a serious problem anymore, there's no attempt to do anything about rivers here. Another guy actually, if somebody really believes in this non-foggy writing and starts to use only 3- and 4-letter words, then again you see rivers, because at the end, if you have all 3-letter words, they're going to line up. There's going to be a white space near the margin on both sides of the paragraph. You've got to use a few big words once in a while just to kill the rivers. Oh yeah, one more question.
In the example on the screen there, you've got roots through there that involve hyphenation, despite the fact that the best root doesn't use any hyphens.
That's true. There was a penalty associated with this hyphen. That's why 3440 was rather large, because the penalty was added in there. And that probably made this branch if this one had gotten in trouble, then the hyphenation would have been taken. But this branch didn't look too good after we added up all the other things. But it did try the hyphen, because in this particular paragraph, I see, because you're talking about my second pass thing. No, in this case, I manually put in all the hyphens because we were making a lot of tests on this particular paragraph on very narrow sizes, and we wanted to make sure that we would get the truly optimum setting in this one. So we imagined that we were going second pass on this. Otherwise, we wouldn't even have looked at that one. Yeah, but on hyphenation, I didn't say, however, I didn't allow all possible hyphens. After FA, I didn't consider hyphenating, because I have tended to become rather conservative about where hyphens should be allowed. In my own opinion, I believe you should be able to pronounce the fragment of the sentence before looking. And if you stopped after FA, you might have think it meant father, and you would say fa, and then you come to the other and say, oh, fay for it, you know. And so I try to, I would like to try to avoid hyphenations in places that you couldn't pronounce the fragment that you see first without looking on the next page or the next line. Okay, let's meet at 3:30.